Greetings, I am Davide. I am a doctoral researcher under the European Night LiDAR project. You probably heard about LiDAR already. It's just a technique to measure how far away something is. You do this by shooting a laser pulse at something and then measuring how long it takes for that laser pulse to come back. Now, imagine looking at a video, but on the video, instead of seeing the colors of the objects being imaged, you actually see how far away each point of the object is. This allows to infer the shapes of objects quite easily, which does give you a lot of information of how the layout of the space actually is. This is a very important tool in robotics because it makes navigation very easy. Indeed, nowadays, most robots, from vacuum cleaners to satellites, use some form of LiDAR, and as automation progresses, LiDAR becomes more and more necessary in all these technologies. The concept works quite well, but there is one very big problem. If you look at a camera, for example the one inside of your phone, the camera is about yay big, and it's also fairly cheap. It's a small part of the cost of your phone. However, if you do look at LiDAR installations, you can see them, for example, on top of self-driving cars. They are not as compact. They are fairly big installations, about yay big, and they are especially quite a bit expensive. And this is where our research comes in. We want to take this big installation and make it something about yay sized. If you think about phones some 30 years ago, they used to be very bulky and not exactly mobile, but nowadays you can get a device that is fairly small, fairly lightweight, very portable and very smart. This is one of the big successes of integrated electronics, that is the study of the small chips that go inside of your phone, which suggests that we can do the same to LiDAR by using integrated photonics, that is constructing those same chips where we guide the light inside our device. More specifically, my work focuses on the part of steering the beam across the space. This can be done fully on chip by using an optical phase array, which is just a big array of antennas where, by adjusting the phases between these antennas, we can choose at which angle the beam is formed and emitted. This, interestingly enough, can be put on a chip quite easily, but the problem here becomes the fact that you need to be able to control each antenna individually. Now, keep in mind, when I talk about antennas here, I mean devices which are smaller than a single piece of air. So it's not like we can exactly check whether all of the antennas are working perfectly quite easily, because if there's any imperfection inside one of the antennas, it becomes very hard to actually assess it. So this is the big challenge that I'm trying to tackle. I need to come up with good ways in order to implement and control these antennas altogether. Since we are working in the domain of photonics, there are some techniques we can employ to make the control of these antennas much easier. Now think about light going through a prism. If you have a white beam of light that goes into a prism, out comes different colors in different beams. We can use the same concept, because if we go in with a certain color of light and we change the color, the output of the beam is going to have a different angle. We can do the same on chip, which means that if instead of controlling its antennas individually, we just design a chip that changes the phases depending on the color of the light, then we can just change the color of the light.